Good morning. In the last lecture on Hilbert space method and weak solutions, we were trying to introduce the notion of solutions in Hilbert space, and we tried to give an algorithm, what are the steps and what are the things you need to do it. And in the process we have introduced motivated you why we want to do that one. Throughout the course we have motivated, and in particular we motivated by a minimization problem, and in the process the minimization problem was in the space c1 naught of omega bar, and you want to minimize f of v is equal to the minimum of not minimum, and the f of v was integral of grade u, grade v, this is a grade v dot grade v minus integral of f is a given function to you. Okay, and then what we have seen that if u is a solution such that f of u is equal to minimum of f of v is in this also motivated why we considered that space that need not be the space correct space, but we have motivated this one. Then we have introduced in the process a linearization, the first derivative. Everything little was vague, we did not give the definition here, and f prime of u v equal to integral of grade u grade v minus integral of f v, everything in omega. Therefore u is a minimizer, implies you have f prime of u equal to 0. That is equivalent to saying that you have this problem, grade u grade v equal to integral of fv. This should look for all v in c1 naught, and you look for a solution u in c1 naught. And this is called a weak formulation, is a weak formulation. We have to justify other steps which we have given in the last class. That's what we are trying to say. But weak formulation of what? That's what we are going to say that now. And then so that's why we are giving connection to Poisson equation, connection to Dirichlet problem. Okay. So recall the Poisson equation, Poisson boundary value problem, minus Laplacian of u equal to. So I call this is the weak formulation 1, and this Laplacian of f equal to f in omega u equal to 0 on d omega. So this is basically a strong form. This is your PDE. This is also known as strong form, because you have a weak form, so you have a strong form. I want to see the connection between this one. So let u be a solution again. Let u be, you know that under suitable conditions it is there. So let u be a classical solution. U belongs to C2 of omega intersection C omega bar be a classical solution. This is the first you have to check. Both are say this is a weak formulation. The one is a weak formulation of 2. You have to first check if it is a classical, then it is a weak formulation. Classical solution of 2. Then multiply 2 by, because it's multiply 2 by 1, 2 by v in c1 of omega naught of omega bar. Integrate by parts, use the divergence theorem, that will immediately imply grade u grade v equal to f of v for all v. You see, so strong form implies weak form. You have to prove also conversely weak form. Conversely, if U satisfies weak form, satisfies weak form. So this is same as 1. Okay, weak form 1 and u is in smooth. Suppose u is in C2 of omega intersection C1 of omega C of omega bar. You see, you have to show that, you have to prove that u is satisfies the strong form. That's what we say, satisfies 2. So this is just integrate by parts. Integrate by parts. Because u is in C2, you can integrate by parts. Integrate by parts 2 will imply integral of minus Laplacian of u. If you integrate this one, it will become minus Laplacian of u plus f. So I am taking, and then v will go here. The v, if you integrate by parts, and there won't be any boundary term, so this v equal to 0 for all v. That will imply by continuity of u and other things, and you assume f is also assume, of course assume f is in C omega bar. We are assuming that implies minus Laplacian of. This is true for all v. So and that's it. So that is what you want to prove it. So it's, and of course u equal to 0 because u is a solution. This is in omega, this is on d omega. So that means it's a corrective. So 1 is a, therefore 1 is a weak formulation of 2. Weak formulation of 2. This is what you want to prove it. Any weak formulation you give, if u is classical, it should satisfy the weak form, and weak form together with the regularity, it should satisfy weak formulation of 2. In other words, and you see, and but then you see this is the weak strong form and this is the weak form. This is a strong form, this is the weak form, and this can, the strong form can, weak form can exist, but strong form, to derive your strong form, you need extra regularity on u. And if your physical solution, which a minimizer is divided only, defined in terms of the integral. So you will see the minimum function is defined, and that doesn't tell you anything about your first derivative, second derivative. So the assuming a second derivative and looking for a classical solution is a more serious issue, because your solution to this minimization problem may not have the second differentiability at all, and only if there is a second differentiability it will satisfy your strong form. That's why the weak form is more physical in this case. You see, now you want to go to the next step, the how to prove existence. Now, so let me how to prove. This is what are the algorithm which I have described, how to prove the existence and uniqueness. Existence and uniqueness, I will not, these are all, as I said, is some sort of a motivation. You need more machinery eventually, and that's what the next course of partial differential equations, the advanced PDE, how to prove the existence and uniqueness of weak form. So let me start telling you some of the troubles, and then you will see. Yeah, first you want to understand the meaning of these terms. So if you how to understand the meaning, so let me use a color. Meaning that means well-definedness of what? Well-definedness of 1. The weak form. So let me call it here weak form grade U, grade V. I'm repeatedly writing so that you remember that one. Okay, so here we recall the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. Schwarz inequality. So I'm appealing to some of the things from functional analysis. If UV in L2, then that implies the product UV is in L1. That means UV in L2 means integral of mod U square is finite. Okay, integral of mod V square is finite. And the Cauchy-Schwarz inequality tells you that integral of mod UV is less than or equal to integral of mod U square whole power half into integral of mod V square whole power half. So that means norm of UV, this is left side is norm of UV in L1 is less than or equal to this is the norm, this is square integral functions, sorry, norm of U and norm of V in L2. So what you need, so the well-definedness is fine. So since UV in C1 naught, since, so we have this, since UV, that's why we have taken C1 of omega, C1 naught of omega bar. You can verify if you are not familiar, check this is an exercise if you are not familiar. UV is in L2. So all these, therefore these terms are well defined because this is in L2, UV is in L2 and grade U, grade V is also in L2. Okay, because C1 of omega bar, the derivative is also there. So therefore grade U, the product and integral of FV are all finite. You see. So therefore the terms are finite quantities under this assumption. Now let's look at the existence. I'm not going to prove this existence because we don't have the machinery yet. I'm only trying to locate the difficulty. So here we are going to appeal what are called Riesz representation theorem in functional analysis. And you need whether we have sufficient machinery to apply Riesz representation theorem. So I'm only discussing some simple cases. Okay, so a more difficult PDE you can handle, and the distribution theory tells you such things. What is Riesz representation theorem tells you? Suppose H is a Hilbert space. Hilbert space. Okay. And L from H to R is a bounded linear functional. Is a bounded linear functional then there exists a unique, you can identify the linear functionals by elements from H. There exists a unique U in H such that UV is equal to LV. This is true for all V in H. And what is this one? This is the inner product in inner product in H. Okay, so we have, so if you look at your weak formulation, if you recall your weak formulation, you are interested in finding this one, you see. So if we can see an inner product like that, so if you introduce an inner product like this, and if this happen to be a bounded linear functional, then you will get existence of U. So that's what we are going to do it. Thus, define UV is equal to integral of grade U dot grade V over omega, and for all UV in C1 naught of omega bar, because our space is this one, C1 naught of omega bar. Indeed, you can verify it's an inner product. Indeed, you can Indeed, we can verify is an inner product. Inner product on H. On C1 naught. That's not the difficulty. So what's the major difficulty? Let me alert to you. That's the major difficulty. See this space C1 naught omega bar with the above inner product is not complete. With the above inner product is not complete. Product is not complete. You see, that's the one thing. Of course, it's a Banach space under a different norm. Of course, that's what so far we have used. Of course, C1 naught of omega bar is complete and is a Banach space and is a Banach space. Is complete under a different norm, not with the inner product, complete with the supernorms, right? Supernorms. But here we have, and in infinite dimensional space, the norms need not be equivalent. So you are defining C1. That's why the strong functional analysis and other things are coming with respect to supernorms. For example, for norm F in C1 naught is something like you define norm of F in supernorm plus you define the gradient of F norm. You can define such things. And hence it is a Banach space under this. But hence it is a Banach space. This is not what we wanted. We have defined a different norm which suits our formulation. So our formulation is this one. We want, so in this case, the norm of U is nothing but L2 norm of gradient of U. You see, the norm of C1 naught here, this is a different norm, is norm of in L2. So it's a different norm. It's not the super norm. Okay, but this norm is different. This norm is different in C1 naught. So the two norms are different. So with respect to this norm, it's a Banach space, but the space what we want to deal with, because your weak formulation is that one, grade U dot grade V, and this is what. So what do you do with that? So you need to take what are called so if you can do this thing, so what you need here is a completion of C1 naught bar, C1 naught of omega bar with respect to the gradient norm, with respect to the norm of gradient of U in L2 norm. This is what your L2 norm. So with respect to that norm, which let's denote it by X. Yes, from functional analysis we know that x-axis as x-axis, and then the elements are equivalence classes. That's not function spaces now. Elements are equivalent classes. And that's not enough. So the question is that, can we identify X as a function space? Can we identify X as a function space? And this is what is the big picture of function space. So the big picture Yes, via distribution theory and Sobolev spaces. Distribution theory we may give you in the next class, not in a detailed way. I told you this is the material for the next course or anything. Distribution theory or Sobolev spaces. So let me write it, which you may not understand now, but let me write that. Okay, so in that case X becomes a Hilbert space. X is, as I can identify, so X right now is a set of all equivalence classes. That's how you complete your normally linear space thing. So X turned out to be something like that. So let's set of all V in L2 of omega. So this is not understood, where dV by dxi is in L2 of omega for 1 less than or equal to I less than or equal to n, and then V equal to 0 on d omega. But then the big question you may immediately ask, if V is in L2 of omega, what is the meaning of dV by dxi? This is what we need, a concept of. So a concept which we may not in elaborate way, but we will explain to you a concept of weak derivative, and then using weak derivative we define spaces like X and are called Sobolev spaces. Okay, so I may do little bit about weak derivatives and weak notions in the next couple of lectures, but let me do little more something like that, assuming that it is a, so we will stop this portion, we will stop here. So assume X is a Hilbert space. Now assume we can define for V in L2 of omega dV by dx, what in distribution theory as an element in L2. In general, derivative of a function need not be a function. In general, dy by dxi need not be a function. But what I am telling is once in general, because for every function in L2 you can define the derivative, but you will not be able to get it as a function. You will see that later. But you collect all those functions V for which your dV by dxi is also a function, and what we are telling is that the completion X can be identified with this space. So you can identify your thing with only those V for which dV by dxi is L2 of omega, and with that setup now you have a weak formulation telling that one. So now we can show that with this you can have an existence, of course uniqueness also, so we will have a kind of existence. So now look at it, define now LV is equal to integral of FV, and then your modulus of LV for all V in X now, not C1 naught of omega, which is a completion of C1 naught of omega bar with respect to that space. Okay, with respect to the gradient, no, it is not with respect to the no. So for all V in X, this one, and modulus of LV, apply Cauchy-Schwarz inequality. This is norm F at L2 and norm V at L2. but you want to see it is a bounded linear functional. To see bounded linear functional L is from H. H norm is gradient norm, H to R. That means what we need to apply Riesz representation theorem, we need modulus of LV less than or equal to some constant into norm V in, so X here. X. Okay. So you wanted V. So what is norm V next? Norm V where norm V in X is a gradient norm is equal to norm of gradient of V in L2. This is by definition. Okay. Because you know that V is in X, you define grade V in L2. So, but you have only this inequality. And then so thus we need to prove, therefore, to prove that norm V at L2 is bounded by some constant into grade V at L2. This you want to prove it for all V in C1 naught of omega bar, and for all V in so it's enough to prove this, then you will get it, which will imply for all V in X, its completion. And this is provided by what is called a Poincare inequality. So let me give you Poincare in the simple case. Poincare is inequality. Okay. What is Poincare inequality? So for all V in C1 naught or for all V in X, of course X is not understood properly. There X is a constant C positive such that norm of V at L2 is less than or equal to constant into norm grade V at L2. Okay. So let me give you a quick proof before ending this lecture. Proof. Once we prove this, your Poincare L is a bounded linear functional and your thing. This proof is simple. Okay. So let's take n equal to 1, 2. The same proof works for same proof for n greater than or equal to 2. So your domain is a bounded domain. Okay. So you can find a rectangle or a square. You find a square. Okay. Contained like this. So find a square. Okay. So find minus a to a, close, otherwise you take n times. Okay, minus a to a is find a neighborhood closed set k, this contains omega. So I can write, so you have V defined here. So for V in C1 naught of omega bar, so we prove this inequality, for V in C1 naught of omega bar. Then by density, it is true for all X. Okay. So for V in C1 naught of omega bar, extend V by 0 outside, extend V to all of K by 0 outside omega. Okay. So V is given here, and which is a continuous function. So you have is a continuous function. It is 0 here. V is 0 here in this point. So define V 0 here. You extend it. And then this extended function, so extend V, and we denote by the same V. So you can apply V to which is a continuous function, and then it's also different, all properties you can see. So I take any point, so take any point xy here. So I can connect this from here, and this is the point from here. Okay, so and v is differentiable, so you can integrate. Therefore, v of xy, and v at this point is 0. V is 0 here. So that you can apply the fundamental theorem of calculus, you get minus a to x. So I am integrating with respect to x, and you are differentiate dv by dt t of y. Okay, and integrate with respect to t. You see, so I can integrate, and there is this is nothing to do v xy minus v minus a 0 by, and which is 0 on the boundary. Any side you can take it, any integration you can take it. So you just if you want, you can do a small exercise, and you can easily see that modulus of vxy is less than or equal to you apply some constant, you apply Cauchy-Schwarz again, and with one as other function, so you get some number. So I will leave it as an exercise. You Cauchy-Schwarz. So I will get, so if you get it as a function of that one, which you are integrating here. So that first term, there is no x anymore here, and integrate, and then I will get a square. So what you get is that dv by dt, that's nothing but dv by dx at dot, with respect to dot y, okay, square. And this is with respect to x variable you are integrating. So no, this is okay. So if you square it, you get this square by Cauchy-Schwarz. Now integrate with respect to y. So left side, what you get it, integral vxy. This exercise I am basically doing it. Dy will be, so you integrate with respect to y also. Already you made an integration with respect to x, and that will give you less than or equal to some constant, etc. will come, and one derivative only coming, so that can be bounded by all derivative. Now there is no x here, do again integrate with respect to x. That's all. Please do this, complete these exercises. With respect to x implies norm of v at L2 is less than or equal to constant into norm grade V. So we have all the setup except understanding x properly. So once you know how to define x, you have your Riesz representation theorem to basically prove this result. So that's it. So then you can define, so by Riesz representation theorem, there exists a unique u such that grade u, grade v equal to fv. This is true for all v in x now, with u in x. And this is very careful. U need not be a smooth function. So u is in x. So not u need not be differentiable. U in general, u need not be differentiable. Okay, in general I am telling. Okay, so you need, in fact, one can study the problem. In fact, one can study the problem with more general, study the problem with general f, with f in L2. So you see, so the whole theory in L2 of omega, the whole theory in the classical theory, we assumed f is elder continuous to solve the problem. So in this setup, you don't need it. So in the generalized setup, I can solve the problem with just f in L2. In fact, I can have a bigger space, bigger other Sobolev spaces where it is need not even be function. So I will be able to study such big formulations in very, very general theory, like regularity. Then of course, if f is smooth, show you have regularity, you have more smoothness. More smoothness. This is what regularity results, and then give classical solution. So I will stop here these lectures. So in the next class, what we will do, we will try to motivate you how to define weak derivatives. As I said, we will not be giving a complete lecture on distribution theory, but we will give you the glimpse of or the motivation behind distribution theory in the next couple of lectures, so which will motivate you to study PDE and the further analysis. Thank you.